Welcome to the University of Sheffield Advanced Manufacturing Research Centre here in Sheffield. My name is Chris McHugh and I'm the Development Manager, part of the Composite Centre. Today we're going to host the tour which includes the Factory of the Future, which is where we are now, the Forge department, which houses our braiding facility, and also Factory 2050, which hosts our press facility. Today we're going to have a team of expert engineers talk about these these pieces of technology and give you an insight into some of the capabilities that we have here at the AMRC. First of all, we're going to have a short introductory video of the AMRC before we're going into the actual virtual tour, and then we'll have a Q&A session at the end. During this session, please feel free to ask questions. The actual virtual tour will be video recorded and we can present this after the event. So thank you very much. We'll now go into the video and then on to the technicians and the rest of the tour.
Hello everyone and welcome to the Composite Centre. My name's Jodie Turner. I've been a technical lead at the AMRC for quite a while now, and I'll be giving you a tour of some of our textile equipment. So this building was a purpose-built extension of the original AMRC built in 2012. Despite the fact that it was purpose-built for us, we have since grown massively and we are spread across numerous buildings, and some of my colleagues will show you amongst other ones. So if we start with our very first piece of textile equipment, the Dobby weaving loom. Come this way. So this is our Donia P2 weaving loom. It was the first piece of textile kit that we did get. So what we can see carbon yarns coming from the materials store on the creels at the back, and they converge together at the back of the weaving machine. We then have a series of shafts which lift and lower those yarns in a sequence that we would program. And then from the side, additional material is fed through that cavity that is made by the lifting and the lowering. This is called the weft. And then if you were to come around the front, you would see that the result is a woven piece of fabric, just here. So this machine is designed traditionally to create a planar piece of material, but we've really pushed the limits of what you can do with this machine. And one of the things that we've made with it is a 5-layer thick piece where every layer is interconnected with the next layer, something that we would call 3D weaving. So I'll show you a piece that we made. So here we have a subscale floor panel, and it consists of multiple different types of weaving in different sections, but it is 5 layers thick. The original manufacturing method for this included multiple layering of almost tiles, if you like, which involved a lot of labour. But through this technology being applied to this manufacturing, it was able to be created in one single piece. So using these advanced weaving technologies, there's plenty of clever things you could do. So we could create, as I described earlier, we could create a single piece of multiple layer where all the layers are interconnected, or you could weave them at the same time but leave them layers not connected. So for example, this is a one-piece woven kit where in these areas the layers aren't connected, but then here they are. And using that sort of concept, there's no end of different shapes that you could make. Here we've got T-sections on T-sections as an example. And here we wove, and this has been formed into composite, we wove a honeycomb. But if you were to adapt that honeycomb slightly differently, you could have something like this, which we created this because it's an auxetic structure. This structure under tension would actually expand in that direction. So it's not just about getting multiple layers at any one time, you can create all sorts of different shapes. So once we'd pushed that Dobby technology to the limit, we then acquired our next weaving machine, the Jacquard. So we'll go take a look at that and look at the differences. So the industrial developments that we had using our Dobby weaving machine naturally led us to acquiring our first Jacquard weaving machine. Whereas the Dobby weaving machine would take the carbon yarns and lift and lower them as a group using shafts, this machine actually has these bright yellow things here, they're called cords, and they control every single carbon yarn individually. So the limited control that we have with the Dobby machine, we've got the ultimate versatility here. As well as the ultimate versatility in yarn control, the differences between the Dobby machine and this one, the Dobby machine has 1,000 carbon ends that fill into the weaving machine. This machine has 3,072, which you can see just around here. So all 3,072 of those carbon yarns had to be threaded up by hand in such a way where no one yarn crossed another, as that would cause filamentation during the weaving process. That took a team of 4 of us upwards of 8 weeks to achieve. So using the increased versatility of the Jacquard weaving machine, we've been able to create some pretty snazzy structures. This is an example of one. It's essentially a planar structure, but within it we have channels, if you like, through which we can put pipe work, and those channels can vary across the length of that fabric. One of the most recent things we made was this blade as a demonstrator. So this varies in width, it varies in thickness from the root to the tip, and it has curvature. Really looking forward to the next steps with that project. This is our final piece of textile equipment here in the Composites extension. This is the tailor fibre placement machine. This machine is essentially a piece of embroidery equipment. So we all know that embroidery creates logos and images on our clothing. Well, what this is doing, it's using that same stitching technology, but instead of creating a picture, it's stitching carbon down to a substrate. So using this technology, we can program it to position the carbon in exactly the right place that we need it to be to serve its load. Not only can you put carbon down though, some of the most recent things that we've done, we've embedded sensors, pressure sensors, optical fibres, thermocouples into our components. So just looking at these, for example, we can see all the different shapes that we can make from the tailor fibre placement machine. We can also reinforce holes of any size. We've got another example here. And this panel that we've made here, this has got optical fibres within it in all different locations. It's then been infused, and those optical fibres serve to provide real-time strain measurements. So that's it for textile equipment here in the Composite Centre extension, but we do also have the braider down in another building. We'll show you a video for that subsequently. But just now I'm going to hand over to our colleagues who's going to talk about some of the automation kit we've got here for composites manufacturing. Thank you.
Hi everyone, I'm Callum Dickinson, research engineer in automation at AMRC. This is our automated fibre placement machine, a long-standing bit of kit at AMRC. And it's been upgraded many times over the years. So for those of you not familiar with this piece of kit, this is for laminating fibre reinforced narrow tapes onto three-dimensional solid tooling. We have various different heads that can be mounted on the robot for processing different materials such as thermoset, prepreg tapes, thermoplastic prepreg tapes, and dry fibre tapes as well. In recent years, this machine's been upgraded with a laser heating system, which is an efficient and responsive method of consolidating particularly high temperature thermoplastic tapes onto 3D geometries. So there's a number of benefits to being able to consolidate tapes onto the tooling with this machine. We can add and cut tapes wherever we like to create a tailored layout. We can absolutely minimize wastage of material in this way. The other benefit is that we can actually steer the fibres on the laminate and add some amount of in-plane curvature, which is really crucial for designing very lightweight next generation aircraft with fibres very well aligned to the load path through the components. AMRC are conducting key research into the design and analysis tools for creating these curvilinear laminates so that this new process can be applied in industry. This is AMRC's robotic pick and place cell. It was installed in 2017 as part of the Lightweighting Excellence Programme for research into high volume processes for the automotive industry. It's been upgraded over the years, and we've added a CNC conveyorized ply cutter, and more recently we've built a 60 gripper matrix end effector, specifically designed for dry fibre applications, where we can pick up plies of roughly 1 metre by 1 metre. So in this matrix gripper we've constructed here, we're using compressed air powered grippers to generate a suction force, which is these type of grippers are very effective for porous dry fibre textiles, but the compressed air usage can be quite high. So to investigate the sustainability of such a process, we've compared this with another type of gripper we've recently invested in, which is the electronic needle grippers. These have a significantly lower energy use, but there are some concerns around the damage of the needles penetrating the fibres in the fabric. We've done some mechanical testing and characterization work on this, which should be helpful for the design of high-performance components in aerospace and automotive industries. What we can do with the CNC ply cutter and the robotic, the pick and place robot, is we can build flat layups from cut pieces of fabric to be later used in a forming process. So we've done things such as building a layup onto a diaphragm film, which is later then used in a diaphragm forming process. We've also laid plies directly into an RTM tool, for injection with resin.
Hi, I'm Carl Hyman, the filament winding research engineer at the Composite Center, and this is our MF Tech high tension filament winding robotic system. This uses a 6-axis KUKA robotic arm with additional mandrel and delivery eye rotation, and is capable of winding up to 4 toes at 180 newtons per toe. Tooling weights can be up to 2 tons, up to 4 meters long and 1.5 meter in diameter. We're able to process a wide variety of materials, including thermosets, thermoplastics, and dry fiber winding. Thermosets can be used in a traditional wet winding process, or they can be used in pre-impregnated toes, whether low-cost toe pregs or high-performance slit tapes. Thermoplastics can be processed with our Heraeus flash lamp technology, or they can be wound and later consolidated in an autoclave. Filament winding is ideally suited for axisymmetric parts such as pipes and pressure vessels. However, we also can wind other geometries such as constant cross-section spar parts or pipe elbows, or even more complicated shapes. A simultaneously driven headstock and tailstock allows us to use fragile mandrels, which are often required for complex geometry parts. Additionally, we can place up to 4 tons of tension on the mandrel, which allows us to reduce the whip encountered with long, thin mandrels. Our IR heater lamps can be used to improve the tack and processability of prepregs, but it can also be used to cure parts on the machine for parts where we don't need a full oven or autoclave cure cycle. We also have a fiber placement head in addition to the filament winding head, which allows us to offer a lower cost alternative to traditional automated fiber placement systems by allowing the use of toe preg rather than slit tape materials. Applications of filament winding varies, with significant uses in the automotive and aerospace sector. We've had a lot of significant interest recently on hydrogen pressure vessels, but we also do a lot of work on fuel pipes, electric motor components, and structural vehicle components.
Hello, I'm Sam Ashworth, a research engineer here at the Composite Center. This is the DMU 340 gantry machine. This was commissioned in 2019 and is one of our most recent acquisitions, and it represents the cutting edge of machining in composites. This machine is a linear-driven 5-axis machining platform. The bed encompasses a 12-meter cubed working area, so that's designed for large composite machining, suitable for aerospace components, tool and mold making. The bed is a single cast platform. The thermal stability control and the HSK 63 spindle allow machining accuracies of up to 10 microns. The linear drives allow traverse rates of up to 90 meters a minute, with accelerations of 3 meters per second squared. The machine allows several coolant options with MQL coolant, flood coolant, and dry extraction through a novel blowing system. The CNC machine is powered by a Siemens 840D controller unit. This is very special because it includes a lot of control monitoring to allow greater accuracies in machining. The tool holder has 63 pockets, so this allows for a fast turnaround of parts requiring different tooling, so drilling or milling cutters. As well as being able to cut titanium, composites, ceramic composites, carbon fiber composites, this machine also has a capability called ultrasonic assistance. So power is transferred from this stator to the rotor wirelessly. Then as this rotor is spinning and receiving power, a small piece of electric crystal pulses up and down, and then this is transmitted down the ultrasonic horn to the tip of the tool. So this is known as a high frequency, low amplitude vibration, which interrupts the cut and provides a different cutting mechanism to conventional. The advantage of this is that we can potentially machine faster, therefore being more environmentally friendly, and we can also change the cutting process to get a higher quality cut, so less delamination in carbon fiber composite holes and a higher quality in ceramic composites. I'd like to introduce the Flow Aquareese abrasive water jet cutting machine. So this is a 6-axis serial linked robot, a Stavely TX200 robot, which has got an abrasive water jet cutting head connected to the end, So this is perfect for machining of composite materials, so carbon fibre composite materials, titanium materials as well. Because of its high traverse rate, it's perfect for roughing operations, so cutting very quickly at a low cost. So this is the abrasive water cutting head. So water of up to 6,000 bar pressure is supplied to this cutting head, which then flows through a mixing nozzle and comes out of the cutting nozzle at the end. The pressure of the water drags through abrasive as well, so that creates an abrasive water jet, which enhances the cutting quality of the machine. So here we have the CMS Aries machine. So this is a machine with a very large working volume. The doors open all the way, so you can fit large components in there. So this has got a very high spindle speed of 24,000 RPM. So that's perfect for cutting composites, mould tools. And this is also a FANUC controller, so this is widely seen in industry. And so what we can do here is replicate industrial practices and make recommendations for lightweighting purposes. Here we have the CMS Antares. So this is the little brother to the CMS Antares, which we've seen. This is also used because of its high working volume, its high spindle capacity, and again we use this for making composite holes, composite milling. So we use a lot of tools on here for toolware trials, so that we can inform industry of the best tools to use and make them more productive, so that they get more efficient processes, which helps to keep costs down. I hope you've enjoyed the tour of the composite machining facilities. If you have any questions, please do send me an email at s.ashworth@amrc.co.uk. Thank you.
Hello and welcome to the press facility. My name's Darren Wells. I'm the technical lead for compression moulding and RTM technologies, and I'm going to take you on a tour of this facility, which was established in 2017 and houses the majority of our composite curing technologies. Starting with the more traditional ways of curing composites, we have two autoclaves and a convection oven. The first autoclave here is our large autoclave by LBBC. It's 3 meters in diameter and 5 meters long. It has temperature capability up to 210 degrees C and can apply 10 bar of consolidation pressure for consolidating parts. Next to that we have the small autoclave, again by LBBC. This is 1 meter in diameter and 2 meters long. It has increased temperature and pressure capability of 400 degrees C and 20 bar respectively. Finally, next to that we have the Caltherm convection oven. This is a 3 meter by 3 meter by 3 meter box. It has temperature capability up to 200 degrees C, and inside it has a vacuum rail for connecting vacuum bagged parts, which is driven by an external vacuum pump. In the middle of the room is our high pressure resin transfer moulding technology by Krauss-Maffei. This is production spec industry standard equipment used most prominently in the high-end automotive sector by the likes of BMW, Volkswagen Audi Group and others to manufacture cosmetic and structural parts at high rate to reduce vehicle mass. The secret to the high production rate is the way the machine mixes and doses highly reactive resin systems using a complex impingement mixing head that would ordinarily be installed in a matched die metallic tool. When running in standby mode, the resin and hardener streams are pumped from the silo tanks at the rear of the machine through steel pipework to the mixing head, but are kept apart via a steel pin which sits in the mixing chamber. When a shot is called for, the pin hydraulically retracts to allow the two components to mix at high pressure, hence the name, and exit the bottom directly into the tool cavity. When the shot is finished, the pin is forced shut, and with tolerances being so tight that it self-cleans the chamber and separates the two streams ready for the next shot. This particular equipment was unique when it was manufactured, as it was a first by Krauss-Maffei to link two different machines to feed two different mixing heads. That gives a massive range of capability from a single unit delivering just 16 grams per second of resin over to two units combined in parallel, giving over 400 grams per second of resin. It also gives the flexibility of having 4 different mixing heads producing 4 different flow rates. Onto our compression moulding capability, and first up is our Langshauser lab press. With a platen size of 1.5 metres along and 1 metre in depth, with pressing capability up to 3,000 kilonewtons, this is an ideal press for proof of concept capabilities. Its real strength is in its programmability and its flexibility, and we've developed some real novel processes using this piece of equipment. 2 such processes were recently covered in a SAMPI journal, namely double diaphragm forming and wet compression moulding between diaphragms. There are many advantages to pressing pre-preg material or catalysed resin and dry fibre by first encapsulating it between polymer diaphragms. The diaphragms create a resistance on the material inside to aid forming of complex shapes, as well as creating a barrier between the material and the tool, leading to fast turnaround of parts due to much reduced cleaning and releasing activity. The quality of part between pre-preg and wet compression moulding using this technique is almost indistinguishable, with the added benefit of being able to tailor the film to give either a gloss or a matte finish due to the component. We have recently increased capability in this area with the addition of an automated material handling system, which takes frames loaded at the front through to the infrared lamps at the rear for preheating, and then aligns it over the tool for pressing before positioning it back at the front of the machine for unloading. Finally, we have the pièce de résistance, the big daddy, the 10 meganewton press by Rhodes. With a ring frame construction, we have 2 independently controlled 3.3 metre by 2.3 metre platens in conjunction with a common top platen. Allows that proof of concept idea to be taken a few steps closer to production. The far platen, which is in the press at the moment, along with the top platen, can be heated up to a maximum of 280 degrees C by thermal fluid. The other side of the press has a much lower platen for use with large multi-piece tools. In that case, we can enable the side loading rams and the end rams to hold the tool in all 6 sides. Hope you've enjoyed the tour of the press building. For more information on any of the kit, please be sure to check out the capability brochure on the AMRC website or drop me an email. Thanks for looking.